Record on the screen. Hello everyone, welcome back to my channel. As you all know that I'm Pratibha SR from 3rd SEM in Electronics and Communication Department at Sri Venkateshwara College of Engineering. Today I'm here with the new topic called as Z transform and its applications, which is related to the mathematics of 3rd SEM. Firstly, let us go through the introduction of the Z transform. The Z transform is a mathematical tool which is used to analyze discrete time systems. It converts it converts a discrete time signal into the complex frequency domain representation. The Z transform is widely used in digital signal processing and the control systems. Definition and the properties of the Z transform. The Z transform is defined as the summation of a sequence multiplied by the complex exponential. It provides a coincident way to repeat and analyze discrete time signals and the systems. The Z transform has several important properties. The properties such as linearity and time shifting. The Z transform properties are F1 of n into F1 of 2, it is equals to summation of m equals to 0 to infinity F1 of m into F2 of n minus m. It is called as convolution definition. And F1 of Z of F1 into n into F2 of n, which is equals to Z into summation of m equals to infinity 0 to infinity F1 of m into F2 of n minus m. Take Z transform. And the Z transform definition is given and the interchange summation. Now, the Z transform and the frequency response. The Z transform allows us to determine the frequency response of the discrete time systems. The frequency response, it indicates how the system responds to the different frequencies. By analyzing the Z transform, we can understand the system's behavior in the frequency domain. The Z transform and the frequency response estimations is given in the respective figure. Now, the Z transform and the transfer function. The Z transform is closely related to the transfer function of a discrete time system. The transfer function, it describes the input and output relationship of the respective system. By applying the Z transform to the difference equation of a system, we can obtain its transfer function. The Z transform of a discrete time signal. The Z transform of a discrete time signal, it is defined as x of z equals to x into n of z. This is analogous to the circuit CT Laplace transform and it is denoted by x into n power z. It is equals to x into z. Z transform and the digital filters. The Z transform plays a crucial role in the design and the analysis of the digital filters. It also allows us to repeat and manipulate filter characteristics and the frequency domains. By applying the Z transform to the filters transfer function, we can determine its frequency responses. Digital filters. A CT step excitation is not an impulse. So, what should the correspondence between the CT and DT excitations be now? If the step excitation is sampled at the same rate as the impulse response as sampled, the resulting DT signal is the excitation of the DC system and the responses of the DT system is the sum of responses to all those DT impulses. Now, Z transform and the stability analysis. The Z transform, it can be used to analyze the stability of discrete time systems. By examining the poles of the system's transfer function in the Z domain, we can determine its stability. Stability analysis is essential in ensuring the proper functioning of the digital control systems. Stability and the Z transforms. Last time we explored sampling and reconstruction of the signals, and we have been saw the examples of the phenomenon, and this known as aliasing. Z transform and the signal reconstruction. Z transform, it enables signal reconstruction from its samples in the discrete time domain. By applying the inverse Z transform, we can obtain the original signal from its Z transform representation. This is useful in various applications. The various applications such as audio and image processing. Examples for the Z transform: let us consider generation of new discrete time signal from Fk to Gk, where Gk equals to Fk minus F of k minus 1. Recall the linearity and the shift, then the equation can be written as G of Z equals to 1 minus Z power minus 1 into F of Z. And Z of cos omega naught kt, it can be written as cos omega naught kt equals to e power j omega naught kt by 2 plus e power minus j omega naught kt by 2. Finally, let us see the conclusion of the Z transform. The Z transform simplifies the convolution operation in the discrete time domain, and the convolution in the Z domain, it involves the multiplication of the Z transform representations of the two signals. This simplification allows for efficient analysis and the implementation of discrete time convolution. The Z transform, the inverse of the Z transform is given as Z inverse of Z square by Z minus A into Z minus B. It is related to the convolution theorem. Z transform and the system identification. The Z transform is used in the system identification in order to estimate the parameters of a discrete time systems. By manipulating the Z transform representation of input and output data, we can determine the system parameters. System identification, it is crucial in modeling, control, and optimization of discrete time systems. Conclusion: the Z transform is a powerful mathematical tool for analyzing discrete time systems. It allows us to understand the system behavior in the frequency domain. Its applications include digital signal processing, control system, and the system identification. Thank you.